Two of the logarithmic differentiation worksheet. I guess on this page, really, all I'm doing is logarithmic differentiation, whereas on the first page, I did a few other things. So the idea for all of these is you could probably find the derivatives without, well, for some of them you could without using logarithmic differentiation, but for a lot of them, it'll make it easier, and for some of them, it'll make it possible. So the trick is, instead of thinking about this as the derivative of some function, think about it as y equals this thing. And so if y equals all of this stuff in the parentheses, the natural log of y would be equal to the natural log of all this stuff in parentheses. So x squared plus 1 to the third power times x cubed plus x to the fourth power. I went a little overboard here. X squared e to the x cubed, e to the x plus x cubed, and times 2 to the x plus 3 to the x, again, cubed. Okay, so this was kind of stupid, but fine. Y equals all this stuff, so the natural log of y equals the natural log of all this stuff. Why is that useful? Well, because you can use your log rules to break this up into the natural log of each of these different things. The natural log of something times something is the natural log of the first thing plus the natural log of the second thing. So all these multiplications I can rewrite as addition. Furthermore, I can take any of these exponents and bring those down in front of their respective natural logs. What I'm saying is when you apply a bunch of log rules on the right-hand side here, you get 3 natural log of x squared plus 1 plus 4 times the natural log of x cubed plus x plus 3 times the natural log of x squared e to the x, which actually I could break up a little bit further. Maybe I'll do that here. 3 times the natural log of x squared, 3 times, okay, how about this? 3 times, open up some parentheses, and then for that x squared, I can bring the 2 down in front, so 2 natural log of x plus the natural log of e to the x. That all came from this term. And then plus 3, what am I on this term now? Times the natural log of e to the x plus x cubed. And I'm missing a few terms, so maybe I'll write those down here. I'm up to this term, so I got 3 times the natural log of 2 to the x plus 3 to the x. And I guess that's everything. Do I got all my terms? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. The purpose in doing all this, I haven't done any calculus yet, but it's a lot easier to take the derivative of sums than it is to take the derivative of products like this. So now what I can do, take the derivative of both sides of the equation. The derivative of natural log of y is 1 over y times y prime. And the derivative on the right-hand side here, well, I got 3 times. The derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. Similarly, the derivative of 4 times the natural log of x cubed plus x is 4 times 1 over x cubed plus x times the derivative of x cubed plus x, which is 3x squared plus 1. Then I got plus 3 times 2, which is just 6. I guess I can just write 6. Times the natural log of x, which is 1 over, the derivative is 1 over x, plus 3 times the derivative of natural log of e to the x. That's just x, and the derivative of x is just 1. So I don't know, maybe 3 times 1 just to really emphasize that I didn't forget about that thing. Plus 3 times the derivative of the natural log of e to the x plus x cubed is 1 over e to the x plus x cubed times the derivative of e to the x plus x cubed, which is e to the x plus 3x squared. And hopefully I can squeeze in this last one here. I just did this guy, so I'm up to this one. I got 3 times 1 over 2 to the x plus 3 to the x times, and yeah, this is really starting to run into itself, so let me kind of wall this off. What goes inside these parentheses right here is the derivative of 2 to the x plus 3 to the x, which is 2 to the x natural log of 2 plus 3 to the x natural log of 2. This is not your answer. 1 over y prime is equal to this stuff. So y prime is equal to y times all this stuff, which, let's see, 3 times 2x is 6x over x squared plus 1 plus, and then here I got 4 times 3x squared plus 1, so maybe I'll call that 12x squared plus 4 divided by divided by x cubed plus x. That's this whole thing, plus 6 over x plus 3. That's this 3 right here, plus 3 times e to the x plus 3x squared, all divided by e to the x plus x cubed. That was this term. And then my last one here, I got plus 3 times 2 to the x natural log of 2 plus 3 to the x natural log of 3, all divided by 2 to the x plus 3 to the x. And technically this isn't even my answer. I got to replace y with all this stuff. So maybe I'll even write that. Replace y with all that stuff. So this y right here. I'm just too lazy to write that all in there. But all this stuff times all this stuff would be the derivative. Oh man, I'm really going to do this 3 more times. Okay, so this derivative here, same basic idea. I'm going to get the natural log of y is equal to the natural log of all this stuff, which I can write as 2 natural log of x plus 1/2 natural log of 2x to the 5th plus 3x plus 1 minus 1/3 times the natural log of x plus x. So what did I do there? I took the natural log of both sides of the equation. There's y equals all this stuff. And then I applied the first log rule to break these up into 2 different logs. Here's one of them, here's the other. I applied the second log rule to break this up as into this log minus this log, which puts all this down on the bottom. And then I applied the third log rule a few times to get rid of exponents. So like this 2 went down in front, this 1/3 power went down in front, this square root brings the 1/2 power down in front. And x e to the x, that's something times something, so I can apply my first log rule again. So I get the natural log of x plus the natural log of e to the x, but the natural log of e to the x is just x. Anyways, this is what you end up with here. And when you take the derivative of both sides, you get 1 over y prime is equal to 2 over x. That's 2 times the derivative of natural log of x, which is 1 over x. Plus, all right, this is cutting out a step, but I think you can follow it. 10x to the 4th plus 3 divided by 2 times 2x to the 5th plus 3x plus 1. What did I just do right there? Okay, the 1/2 hangs out. That's this 2 down in the denominator. The derivative of natural log of all this stuff is 1 over all this stuff. That's why it's all down in the denominator. But then I'm not done. I have to multiply by the derivative of all this stuff, which is 10x to the 4th plus 3, which I threw up here in the numerator. From that, I want to subtract 1/3 times the natural log of x plus x. So minus, I don't know, 1 over 3x minus 1/3. One way you could write it. Natural log of x, its derivative is 1 over x. And that 1 over x and the negative 1/3 gives me this term. Derivative of x is just 1. That gives me this term right here. So y prime is equal to y times all of this stuff right above it. Again, I'm being a little bit lazy. I shouldn't leave a y in there. I got to substitute, replace y. I just don't feel like it. I don't have room to do it. Let's not sound lazy. I don't have room. That's my excuse. Okay, this thing, you've seen this problem before. It was damn near impossible before. It's still pretty close to impossible, but it's a lot more doable now. The idea here is I will say that the natural log of y, same thing. I don't want it in green. I think I've seen too much green here. Maybe I'll make it blue. The natural log of y is equal to, and then if I use a whole bunch of log rules over here, I can take this 10 down in front of the whole thing, and then I can multiply that by the natural log of the top here. Well, it's all raised up to the 1/10 power, so I can bring that 1/10 down in front. And then I got the natural log of the top minus the natural log of the bottom. So the natural log of 10x to the 10th plus 10 e to the x. And I want this 1/10 to get applied to both this and the natural log of x times 10 to the x power, which I suppose I could write as the natural log of x plus x times the natural log of 10, if I felt like it. Make sure all my parentheses are right. This 1/10 has to hit all this stuff. So these parentheses close here. And then this 10 has to hit all this stuff and more stuff. So I don't want to close these parentheses just yet. From that, I want to subtract, taking care of everything up top here. Now I got to worry about the bottom. I can bring this 10 down in front and say it's that times the natural log of 10 minus 10x minus the natural log of the bottom here. Natural log of, and I'm a little bit short on room, but I'll try to squeeze it in, 10 raised up to the 10x plus 10 power minus 10. Close these parentheses. Now I want to close this 10 parentheses for this exponent. And now finally I want to close these big parentheses for this 10 right here. Using all of my log rules, this is what this problem breaks down to. And the nice thing about this is I can take this derivative a lot easier. The derivative natural log of y is 1 over y times y prime. And then over here, the 10 is just a constant. Should I distribute a little bit before I go taking derivatives? I guess it's kind of up to you, but sure, I'm gonna do it while I go. 10 times 1/10 is just 1, so I don't have to worry about that. The derivative of the natural log of all this stuff is 1 over all this stuff, 10x to the 10th power plus 10 e to the x, times the derivative of all that stuff, which is 100x to the 9th power plus 10 e to the x. So this first derivative I've got here. This one here, I have to be a little bit careful because this 1/10 should apply to it, but also this 10th, but fortunately those cancel out. So I just need to subtract. And then the derivative of all of this stuff, well, the derivative of natural log of x is 1 over x. And the derivative of x times the natural log of 10. Natural log of 10 is just a constant, and the derivative of x is just 1. So I would get minus the natural log of 10, minus coming from the fact that I was subtracting all this stuff here. So this is what I have so far. From that I want to subtract. I have this 10, but this 10 also has to get applied over here through the parentheses. So really I have minus 100 there. And the 100 gets multiplied by the natural log of 10 minus 10x. So the derivative of 10 minus 10x, let's see, how should I write this? Sure, so I'm going to say minus 100 times, and then the derivative of 10 minus 10x is 1 over 10 minus 10x, times the derivative of 10 minus 10x, which is just negative 10. So that makes this a positive and throws a 10 up here. That's the derivative of all of this stuff. This 10 has to hit this term, but so does this 10 right here. So really there's a 100 floating out in front here, and I'm subtracting this negative, so really it's positive. So I get that it's plus 100 times the natural log of all this stuff, which is 1 over 10 raised up to the 10x plus 10 power minus 10, times the derivative of this stuff. The derivative of 10 raised up to the 10x plus 10 power is 10 raised up to the 10x plus 10 power times the natural log of 10 times the derivative of 10x plus 10, which is just 10. And then from that you have to subtract the derivative of 10, which fortunately is just 0, so I don't even have to write it. I think my final answer ends up looking something like this. I could say y prime is equal to y times all the above stuff. And really by y, maybe I'll illustrate that I mean all of that stuff. This entire thing. I just don't want to write it again. Okay, I've come this far. Fortunately, these last few are a little bit easier. These last three, it turns out they're impossible unless you use logarithmic differentiation. There's no rule for x to the x power that we have, but if you set it up as y equals x to the x power, you can take the natural log of both sides of the equation, and apply your third log rule to get that the natural log of y is equal to x times the natural log of x. And now I can take the derivative of both sides of the equation. The derivative of x times the natural log of x, I'd have to use a product rule and get 1 times the natural log of x plus x times 1 over x. So I get that y prime is equal to y times the natural log of x plus 1. This all simplifies to just 1. But I shouldn't leave a y in my answer since I just made that up. That's x to the x power, even though I've been doing that throughout this video because I've been a little bit lazy. I would say that this right here is the derivative. Just substitute what y is equal to get here. Same basic idea for this next one. I'm going to set it up as y equals this stuff. So y equals the sine of x raised up to the sine of x power. And again, there's no rules that will deal with this. No, this isn't a chain rule or a product rule or anything. But I can use logarithmic differentiation, take the natural log of both sides so that I can bring this sine of x down in front. So really there's two steps there. Take the natural log of both sides, then apply your third log rule to bring that down in front. Now you can take some derivatives. The derivative of natural log of y, as we've seen a bunch of times, is 1 over y prime. Over here I got to use a product rule. The derivative of sine of x is cosine of x times the natural log of sine of x. Plus the derivative of natural log of sine of x is 1 over sine of x times the cosine of x. And then I want to multiply that by the sine of x for this one right here. And so what I get is that y prime is equal to y, which is the sine of x raised up to the sine of x power, times the cosine of x times the natural log of the sine of x, plus sine of x and 1 over sine of x cancel out, cosine of x. I get this whole mess right here. Same idea here for part F. This might have been a little overkill. It might look like you can apply some log rules to bring this down in front, but it's not the x being raised up to the natural log of x power. It's this entire thing. So no log rules apply. So what I have to do is introduce yet another log to get y equals the natural log of the log base 2 of x raised up to the natural log of x power, so that I can apply my log rule to bring this natural log of x down in front of this natural log of x. Wow, that's a lot to keep track of. Y equals this natural log of x right here times the natural log of the log base 2 of x. All that so that I can, let's say I had to introduce natural log, so I guess I took the natural log of both sides of the equation there. All that so that I can take derivatives. The derivative of natural log of y is 1 over y times y prime. And on the right hand side I use a product rule. The derivative of natural log of x is 1 over x. Leave the rest of this stuff alone. Plus the derivative of this thing, I'd have to use the chain rule to get 1 over the log base 2 of x. That's taking care of this natural log right here. But then you're not done. You have to multiply that by the derivative of log base 2 of x. And the derivative of log base 2 of x is 1 over x times the natural log of 2. And you're still not done because you have to multiply that by the natural log of x for the f in the product rule to get this thing right here. So y prime is equal to, we'll multiply both sides by y being log base 2 of x raised up to the natural log of x power. And then that gets multiplied by the natural log of the log base 2 of x divided by x plus natural log of x divided by log base 2 of x times the natural log of 2. Wow. Okay, last thing on this worksheet before I can end this video and get back to my basketball game is I am supposed to prove the product and the quotient rules. It sounds worse than it is. Just say that y is equal to f times g. All three of these guys are functions. Take the natural log of both sides so that you can apply your first log rule. The reason you do that is now you don't have to use the product or the quotient rules if you're taking the derivatives. So the derivative of the right-hand side is 1 over y times y prime. The derivative of natural log of f is 1 over f times f prime because f is a function. And the derivative of natural log of g is 1 over g times g prime. So what that tells me is that y prime is equal to, if I multiply both sides by y, sure, I'll show it in an extra step, y times f prime over f plus g prime over g. And that doesn't look like the product rule. However, if you remember that y is f times g, I can take this and distribute it through. If I take the f times g and distribute it to this first term, the f's cancel, and I get f prime g. If I take this f times g and distribute it to the second term, the g's cancel, and so I get g prime f. And this right here is exactly the product rule. Exact same logic will work to show the quotient rule. I'll say y equals f divided by g. So the natural log of y is equal to the natural log of f minus the natural log of g. So 1 over y prime is equal to 1 over f prime minus 1 over g prime. So y prime, which is what I was trying to find, is y times f prime over f minus g prime over g. However, now y is f over g, so it's f over g times this thing. And if you take this and distribute it through, let's see, I can get these f's to cancel out. So I would have f prime divided by g minus f g prime divided by g squared. That's this fg distributing to both of these terms. And if you got a common denominator, your least common denominator would be g squared. To make this a g squared, you have to multiply the top and the bottom by g. You get f prime g minus g prime f over g squared. In other words, our quotient rule. Oh man, all right, this video is done.